Hey guys, it's John the Quan here. Quick news first, I am shooting the videos for the Linear Regression Superfast course, so keep an eye out for that. It should be out soon, but today I want to do something a little different. Recently, I was asked to do a data science challenge, the kind of technical challenge that a lot of companies will ask you to do if you've applied for a job with them. And I think my approach was interesting, and I think it was pretty successful. So I thought we'd just kind of walk through that and what I was thinking. And that's what we're going to do today. It shouldn't be too long of a video either. I'm not going to say the name of the company, and I'm going to try to keep any mention of the company out of the video. Hopefully it doesn't show up when we're looking at my code or anything. I don't know why it would. The challenge itself. So essentially we're predicting car prices and also trims. Now, if you're not familiar with trims, there are different levels of the car. For example, we're going to look at this later, a Jeep Grand Cherokee, which I actually used to sell Jeeps for a little while, so I'm a little familiar with the trim packages. And on a Grand Cherokee, you'll start off on the Laredo, I think. And the Laredo will come with cloth seats, and it'll have the smaller screen for the radio, and it won't have the seat warmers or anything like that. And then as you move up, you go through the Limited, and Limited will have, I believe it has the big screen for the radio. It ought to have seat warmers. It'll probably have blind spot monitoring. And did I say leather seats already? I'm not sure. Things like that. And as you keep going, you can go all the way up to SRT, which has all the different comforts, and it also has the automatic stopping, and it's got the big engine so that it goes fast. And there's a lot of really cool stuff going on in a Grand Cherokee SRT. I sold one, and I got to drive around in it and ride in it. It was awesome. But in any case, we're trying to predict the trim packages. So that's going to end up being a multi-class classification problem. And we're also trying to predict the price, which is just a regression problem. The way this came in, I got a training data set, came in as a CSV file, and that had 28 columns of features, and then it had 2 columns that were the answers. It had a column for the trim and a column for the price. And the best part of this project was that the features were super dirty, completely just unclean, and I really loved getting my hands in there and grappling with them. So after I had cleaned everything up and made a model to predict everything, I then had a test data set that had the same 28 features but didn't have the answers. And the goal of the challenge was to build a model on the training data set, make predictions on the test data set, send those predictions back in along with, a description of what I did and why. So let's go over to the computer and we'll talk about what I did and why. Let's get a minute.
All right, guys, we are now looking at my laptop here, and let's see, this is a data science challenge problem, like I said. For imports, I'm going to try to go pretty fast. All right, for imports, I used, Pandas, NumPy, Matplotlib, Seaborn, a lot of normal ones. I also used stats models just for QQ plots. We'll look at that. I ended up just using XGBoost models, a classifier and a regressor right here. These are very powerful for prediction. They're not always right, but they're great models. You see them, they show up a lot in Kaggle contests. Maybe they don't win, but you do see them a lot. All right, I needed a bunch of metrics. I was being graded on R2 score and also the area under the curve, which would have been this one, ROC AUC score. Needed a pipeline. I had one column of stuff that was just text, raw text, so I just threw it into a TF-IDF vectorizer and used that instead of doing anything a little more NLP. I probably could have gotten a lot more out of it, but I didn't. Then I did a bit with mutual information just to kind of see what I was, working with. And I needed a one-hot encoder for categorical variables, a standard scalar for numeric variables, and then a label encoder and label binarized because I had for the trims, that was a multi-class classification problem. So that's what I ended up using for that. I also checked out using PCA and TSNE for dimension reduction. And we'll look at that. It actually ended up pretty cool. Then lastly, I used HyperOpt for Bayesian hyperparameter optimization. Now down here, these three files are full of functions that I wrote, and we're going to talk a lot more about those later. So loading the data, it was just in a CSV file. You can see we had, looks like 27 features and 2 target columns, the trim and the listing price. So just a bit of exploration first. I split it up into dependent and independent variables, even though I didn't end up needing to. I usually like to do this so that I can look at them and treat them separately, because eventually they are going to be separated. So I just kind of started off here by looking at them separately. And look at the missing values there. We had quite a few interior colors missing. Since we only had about 6,000 observations, this was kind of a lot of missing values there. Now, here we go. Explore, clean, transform, and engineer features. If you watch my machine learning process video, then you know that I like to treat all of these as a single step, because I think as you're exploring, you need to be cleaning, and you need to be thinking of those transformations and features you would want to engineer. So I definitely treat this all at once, and I always start with the dependent variables because they're what you're trying to predict. It's very important that they be something you can work with. Now for vehicle trim, so you can see there were quite a few trims, and a lot of these have a lot of overlap. For example, limited is very similar. It's not exactly the same as a limited X, but I've only got one limited X, and I've got 1900 limiteds. There's no way a model is going to be able to tell the difference between those. Or here I've got SRT Night versus just SRT. And the difference between those is pretty much just aesthetic. It might be a slightly different price, but how is the model going to be able to tell if it doesn't have like a picture or something between those two? So those are the kind of things that I'm thinking about when I look at this. Or the limited 75th anniversary edition versus a regular limited. So first thing we needed to do was clean that up. So I just went ahead and looked through a little more in the training data, and I wanted to say, you know, we've got this one that says luxury. It's down here. And then we also have premium luxury. So I kind of wanted to look at the difference between those. So I was looking at the makes based on that, and I found out that I've only got Cadillacs and Jeeps. That's it. Cadillacs and Jeeps, and that's all. And they have purely different trims, purely different trim levels. And so then I was able to go to the Cadillac and Jeep websites and kind of look up a little bit of information about these trims. I did used to sell Jeeps, so I'm a little familiar with these. But I'm very unfamiliar with Cadillacs, even though when I was working at that car rental place, we rented a lot of Cadillacs. I couldn't tell you the difference between trims here. But over here, I've got somewhat of an idea of the difference and how you can kind of pair them together. I know that Laredo and Laredo E are different cars with different prices, but I know that they're close enough together that I don't think a model is going to be able to tell the difference. So I decided to split them up, first by Cadillacs and then by Jeeps, and kind of bundle them together based on what I was able to find out by just researching them. Okay, this is an area in which domain knowledge, knowing something about the cars, is going to be very helpful. So I went ahead and I binned the vehicle trims for Cadillacs into just premium, luxury, base, and platinum. So that's going to erase a little bit of information, such as is it all-wheel drive or front-wheel drive? Or this front-wheel drive one, no idea what that even means. Is that a base model? I don't know. So I just ended up deleting it entirely down here. And I ended up with premium, luxury, base, and platinum, and they're distributed like this. Premium is most popular. Now for Jeeps, we did the same thing, but Jeep has just a whole bunch of different trim levels. So we didn't get to limit it as hard as that. So I made this plot to look at the distribution, I guess, of trims, and I found that limited makes up by far the most, and then Laredo is there, overland, altitude, but everything under Trackhawk is a little more complicated. What does 75th anniversary mean? Or Sterling edition, what exactly is that? Upland, is that close to an overland but just sold in a different place? Like I know the Lone Star edition of Ram truck is the same as a Bighorn edition, it's just sold in a different state. So I decided to cut off everything under Trackhawk. I think Trackhawks are cool, so I kept Trackhawk. And down here, after the trims got all cleaned up, this is what we ended up with. For Cadillac, we had Premium, Luxury, Base, and Platinum. And for Jeep, it was Limited, Laredo, Overland, Altitude, Summit, Trailhawk, High Altitude, SRT, and Trackhawk. And I bundled a lot of those other things together. Now, this is definitely the most questionable thing that I did in the entire project, because if we need to be able to predict 75th Anniversary Edition, there's absolutely no way we're going to do that. If we need to predict Upland, no way. If we want to be able to tell the difference between Limited and Limited X, no way. But again, that was not going to happen with our data anyway. So I feel very justified in making these, in binning the targets like this. Because just based on what the data looked like, there was no way we were going to be able to handle more classes than this. Not with the data that we've got. So then the next thing I wanted to clean up was the price. So I started off by just looking at it here, distribution. And we can tell there's a pretty clear difference between Cadillacs and Jeeps, which I think we should expect Jeeps just to skew a little less expensive, because a Cadillac is seen as a luxury car and a Jeep isn't. However, Jeeps do get very expensive. If you start getting into the SRT Grand Cherokee or even an Overland, they get pretty expensive. So as you can see, most Jeeps aren't as expensive, but there's some pretty expensive ones up here. And even the most expensive thing we've got is a Jeep. And then I said, I wonder if I could make it look a little bit more like it's normally distributed just by doing a log transform. And so I did this log transform. The Jeep does look more normally distributed. And here, this is where I used stats models just for the QQ plots. So this is just Cadillacs. Originally, you could see that they were not very normal. And then after the log transform, it was much closer to a normal distribution there. Jeep's kind of the same, though not as normal. You can see even in our plot up here, that Jeep is still a little skewed. Now, none of this mattered for XG Boost because it's non-parametric. It doesn't care if everything's normally distributed or not. But at this point, I hadn't decided what kind of model to use, so I figured there are some models. There's really two classes of models: the ones that care and want it to be normally distributed, or the ones that don't care what the distribution is. So there's not really a downside to just normalizing your data or making it normally distributed. I defined this quick scale. All this does is basically transform a number into a z-score, subtracts the mean, and divides by the standard deviation. And I said, what if I take the log and then I standardize it? Does that help even more? And it looks very normal. Both looks pretty good, actually, except Jeep is not centered at 0, which is very interesting. So even after I scaled it, Cadillac looks nice. I could definitely use a model that assumed normality on Cadillacs, but I'm not sure that I could on Jeeps. Now, going through the independent variables, or the features. In machine learning, they're often called features, but in statistics, you hear them called independent variables. Now I decided to go through every single one of them. All right, and I split it into train and test sets so that we could look at it in this notebook. I didn't do this in the original where I made the predictions and turned it in, because I handle things differently. But here I figured we want to see how it performed on completely unseen data, so I did this a little extra. Now then, I went through every single feature, and I decided I'm either going to call it a categorical feature, I'm going to call it a numeric feature, or I'm just going to get rid of it. Those are the three kinds of features that we're going to have. And then I went through every single one separately. So first I had the city that it was in. And looking at this, there's a lot of different cities. I didn't figure this was actually going to make a difference, so I decided to drop it. And then the next one, uh, I decided it was way too imbalanced, and I decided to just drop it. And then sorry. If I just keep going, we had um, how many is this? Several different sellers or the listing source, and I decided to bin those into DMI, ICC, HomeNet, Jeep Certified or just Certified, and other. So since I decided to bin it, it's a categorical feature and I saved it. And I went through this. I don't want to talk about every single one, but I went through them all and I ended up dropping quite a few of them. Like, see this one here? Most of what I did, if it wasn't numeric, was I looked at the value counts and divided it by the size. So I could look, see 6% were from Vroom, 4.5% were from Carvana. And I said, this seems like there's too many values with too few. Like, what is this? This is like one listing from Cadillac of Dublin. I don't think that this is going to make any difference, and then I decided to drop it. This one's interesting. Listing ID. I'm sorry, not listing ID. Seller rating. Seller rating is stars, like 4 stars, 4.8 stars, something like that. So it's kind of categorical, but kind of numeric also. So in this case, you just kind of want to decide how to treat it. I looked at this plot here, and I said, you know what I want to do is I want to round them and treat it as categorical, but I also just want to keep it as numeric, and then I can decide which one of those two is more important later. And so keeping going, looking here, this is how many reviews a seller has. I decided to take the log distribution of that to make it look much more normal. Again, didn't matter to XGBoost, but I didn't know I was using XGBoost yet. Save that one as numeric, yada yada. There's, too many states. Actually, I just decided to keep states and use them as categorical variables. Seller zip, there were way too many, and I just dropped it. What I really would have liked to do if I had had more time with this zip code is translate that to longitude and latitude and treat it as numeric, so that we could use the area or the distance between these listings as a way of comparing the price, because as you might know, prices are definitely different from city to city if you're looking for a used car. Everything ended up being an SUV, so we just dropped that. Now, looking at this one, this was the exterior color, and they're very different. These are both black crystal pearl coats, but what's the difference between brilliant versus diamond? You know, so I figure the important thing here, and you'll look at this if you've ever shopped for a used car or a new car, and you look at that listing price, the important things are you get a clear coat that's kind of the base. You can get a pearlescent color or a pearl coat that's a little more expensive. You can do a metallic color that's a little more expensive, and then there's ones that where they don't really tell you, and I kept that as other. So I figure these are the important things to keep. Again, that's some domain knowledge that comes out important. Then looking at the interior color, which if you recall, I don't know why it says Gilbert, but if you recall, the interior color had a bunch of missing values. But look at this, black, jet black. This is obviously both supposed to be Sahara beige, but somebody is just spelling it wrong. Things like that. So I ended up binning that as well into, black, beige, frost, all the way down here. I kept everything down to plum. Anything with fewer than 13 that didn't get binned, I just got rid of. Most interiors are black. Black's a good interior color. Kept that as categorical. Here we had this kind of issue. Does it say 4x4 or does it say four-wheel drive? Those are the same things. We also have ones that say 4 like spelled out. There were ones that said AWD, ones that said all-wheel spelled out. So we decided to bin those as well. keep them as categorical. Then in the engines, same sort of thing. Is it a 3.6 liter? Is it a V6? Is it 5.7, 6.4? This 8 right here, it just said V8. It didn't say what size. So I decided to bin those up like this and keep it as categorical. Now, if you've been paying attention, you would have seen things like this function here, and we're about to go talk about those in a minute. Now, the vehicle features column, this came in as a series of lists. And as you can see, it is just a list of features. So what I ended up doing was going through each one of these and saying, you know what, if it talks about brakes, a lot of them said anti-lock brakes. If it talks about brakes, it gets a 1. If it doesn't talk about brakes in its list, it gets a 0. If it talks about airbags, it gets a 1. If it talks about input, it gets a 1. So I one-hot encoded this list into this new data frame with things that seem important. Cameras, Bluetooth, alloy wheels that you'll pay extra for. This one, this human, is actually aluminum wheels, but some places typed aluminum and some places typed aluminium. So whether or not they had that I after the N would have made a difference. I decided to just use UMIN because that captured everything I needed to know. And there you go. You can see like 93% of them said something about the brakes. And like 15% said, oh, we have a camera. Now, almost everybody used gasoline, but there were some flex fuels and stuff. I decided to keep that as categorical as well. Now, this was an interesting one because the vehicle history, it had an order to it. How many owners was always first, and then whether there was non-personal use reported was second. But if there wasn't non-personal use reported, they just left that out and went straight to the third thing, which was buyback protection eligible. Or something like that. I don't remember exactly. No, it was owners, accidents, non-personal use, and then buyback. So if there were no accidents or non-personal use reported, you only had 2 items in that list. But if there were no accidents, you only had 3 items in that list. And so we had to run through kind of recursively in order to one-hot encode that, much in the same way that we did up here. Then going further down, how long has it been listed? I transformed that using a log transformation. Everything was just Jeeps or Cadillacs. I kept it as categorical, even though I thought maybe I should split this data up into 2 data sets and make a model for Jeeps and a model for Cadillacs, which I think would have been the way to go. But again, this was for, a challenge thing. I didn't want to spend 40 hours on it, so I just kind of left it. And we'll look at how that affected the model later. Now, the mileage, if you looked at how many miles the vehicle had been driven, it already looked pretty normal. It fits well enough on the QQ plot, so I just left that. Now, we only had Grand Cherokees for Jeeps and XT5s for Cadillacs, so this next column, the model column, is literally the same as Cadillac versus Jeep, so we just got rid of it. Now then we had the price label, good deal, great deal, etc. That seems pretty important. I kept that as categorical. Now here we go. This column, vehicle seller notes, is just text. Drop by to see us and you will quickly see how Century's spirit of providing our customers with the highest level of service and product in the automobile industry will make you believe too. Now, there's probably a lot of information. Like, look at this one. Priced below KBB fair value price. Or this one. 2017 Jeep Grand Cherokee Laredo. True Blue. Blind spot or crash path detection. These are things that will give us a lot of information about the trim and the price. But, again, I didn't want to spend a huge amount of time because this is a challenge problem, and you should never spend a full week working on a challenge problem. Okay? You're not getting paid for these. So you should just do something that you can be proud of that isn't too crazy and send that in. So what I did here was I just ran it through a TF, term frequency, inverse document frequency vectorizer and brought it back. And we'll look at how this works here in just a minute. All right, the same thing. They were all used to drop it. Change, they were all some kind of 8-speed automatic transmission. So I just dropped that as well. Kept the year as categorical. And here we go. These are the numeric features, which features are categorical, and which ones am I getting rid of. Now down here, final preprocessing. I got all of the features, okay, whole data, up to the negative third column. So that's all of the features. And then target 1 was the vehicle trim feature, target 2 was the dealer listing price feature, and target 3 was that log price that I did earlier. And right here, preprocessed features, we're going to go over to Sublime Text and look at what that is. So down here, preprocessed features, what I needed to keep in mind was that I needed to do a whole bunch of different preprocessing and cleaning things in the data set. But I also had this test data set that I needed to do exactly the same thing to. So I needed to keep a function that I could just feed the data through that would do all of the cleaning for me and would do it in exactly the same way. So that's what this function does. I actually ended up making 2 functions that do it exactly the same way, but that's what this function does. So I keep track of which features did I want to take the logarithm of, which ones are numeric, which ones are categorical, and which ones I just want to drop. So we just feed in the whole features data set, and it's going to drop everything, and then it's going to use these different functions to bin it. Let's go have a look at this one, bin seller list source. Bin seller list source takes in the series. If it's a missing value, it just says other, and then it codes it to DMI, ICC, HomeNet, or certified. And if it's not in any of those, it returns other. And you see they all kind of follow the same thing. For the exterior color, it says if it's a missing value, give it other. And then if it says pearl, then it's pearl. If it says metallic, it's metallic. If it says clear, then it's clear. If it doesn't say any of those, then it's other. And so on. And this is how I ended up binning everything, was with these kind of functions that clean things up for me. You can see this one, the vehicle history that was ordered but incomplete. Where if there were no accidents, then it was just missing a value for accidents. This one ended up being kind of an in-depth function where I had to loop through, say, if there was a title issue, then based on so if there was a title issue, then I had to cycle through 1, 2, and 3, the other columns, and look for whether it contained anything, and then give it a 1 or a 0. So back down here, after I had binned everything, all right, this one here returned this process vfeats. It returns a data frame, okay, not a that one hot encoded data frame. So I said I need to keep this separate and we'll attach it later. And then I need to drop that column because I'm not changing the column. I'm producing an entirely new data frame. And then process vehicle history was the same way. I needed to attach a new data frame later and then drop that column. And then TF-IDF data. So for this one, it's important to not only fit the TF-IDF vectorizer, but I need to use that exact same vectorizer on the test features. So I needed to return it. I needed it to come out of this function for me. So let's go look at that one real quick. Is this the one? No. Vehicle seller notes is what we're looking for, right? Where are you? I think I called it process TF-IDF. Nope, process vehicle seller nodes. Where are you? Vehicle seller nodes. Oh, there it is. It was short. That's why I didn't find it. So it took in that series, and if it was missing, it just says none. Then I just said TF-IDF vectorizer, max features is 100. I only kept the 100 most important words as determined by that TF-IDF vectorizer. I figured 100 was plenty. Could have kept more, maybe got a little more information out of it or something like that. But I figured this was fine. So create the TF-IDF vectorizer, fit transform the series, and give me that vectorizer back. So then back down here, I've got the TF-IDF data frame and the vectorizer. And then for the numerical features, all right, I'm sucking those numerical features out of the features data frame. And then I'm going through the numerical features. And if I want a log transformation, then I'm making that log transformation. And this is actually, it's not a log transformation, I'm sorry. It's a inverse hyperbolic sine transformation because I had some non-positive values. I had zeros. I had possibly negative numbers. I don't think so, but zeros. And log transformation doesn't work for zeros. Whereas this inverse hyperbolic sine transformation will kind of make things normal. It looks very similar to a log transformation, but it doesn't care if you have zeros. So that's what I needed to do. So that's what I did here. All right. And then for the categorical features, I had to suck those out, and then I wanted to round the seller rating. That's the only one I rounded. And then I wanted to add the owners feature because owners was the first column. It got treated a little differently in this function. I ended up not using this part, so don't worry about this. But then I needed a scale. I needed to scale the numerical features. Again, I hadn't decided to use XGBoost. And then I needed to one-hot encode the categorical features. And I needed that scalar and that encoder in the same way that I needed that TF-IDF. All right, so I need those to come out of the function down here so that I can use the exact same scalar, encoder, and TF-IDF vectorizer on the test features. Now, if we go back up here and look at how I processed the categorical features and numerical features and TF-IDF features, here, in the categorical features, they have to be an object or make them an object. And then if it's unknown, we need to ignore it. This is important because sometimes the test data set might have a new thing that we haven't seen before. For example, if we only kept, black, beige, and blue seats, but then in the test data set they had brown seats, we'd be screwed. All right, so I need this handle unknown equals ignore thing. And then I did a fit transform on the categorical features that one-hot encoded everything, but then I want it to be a dense matrix, not a sparse matrix, so that I can reattach it later to the whole thing. This would not have worked if it had been a very big data frame or a very big amount of data, but I only had about 4,000 observations left over and not that many columns, so this works. And then I need to return that one-hot encoder and the encoded categorical variables. Numerical features is very similar. So just call up a standard scalar, fit transform numerical features, and then just put that back. Now, standard scalar doesn't return a sparse matrix, so I didn't have to worry about that. That was fine. But I do need that scalar back. Now, for the TF-IDF, really all I did here was I changed the TF-IDF data that I got out of the previous function back into a dense array instead of a sparse array, and I gave it its columns from its own vocabulary. So once you've run through those three things, then my preprocessed features, the whole thing, I concatenated the scaled numerical variable data frame, the encoded categorical variable data frame, the vehicle features data frame that I one-hot encoded kind of by myself before, and the TF-IDF data frame right there, and just kind of put those side by side along the column by column axis. And I needed to return, again, the scalar, the encoder, the TF-IDF vectorizer that I made, and the processed features thing. Now, down here, process test features is very similar. I probably could have just made this function a little different and used exactly the same function. For example, if I had just said, scalar and had inputs for scalar and encoder up here, and if I didn't put anything in, then I needed to make one, but if I did put that one in, then use it, then I could have used the same function. But I decided to make two separate functions. This one is exactly the same, but instead of making its own scalar encoder and TF-IDF vectorizer, it uses ones that you put in. So that was a lot. and it was fast, but hopefully you're doing all right. As you can see, we just run preprocessed features on the features data frame that we got from here, and that spits out the standard scaler, the one-hot encoder, the TF-IDF vectorizer, and the preprocessed features data frame. And as you can see here, we ended up with about 4,000 observations and a total of 218 features. We started off with 26 or 27, and we ended up with 218 once everything was done. Now I looked at a bit of feature selection. I tried PCA, but as you can see down here, it was going to take about 55, maybe 57, something like that, features to account for 95% of the variance. And since 218 in the grand scheme of things isn't that many features, I didn't think this was worth it. I decided to just keep everything. I also, like I said, tried a bit of t-SNE transformation. And look at what happens when you plot the PCA and t-SNE transformations in 2 dimensions. PCA, you can see 2 dimensions isn't really getting you anywhere, right? But for t-SNE, looking at this, you could almost just do pretty well at separating the different trims by like support vector classification or something. Look at the spacing on this. That's pretty great. And this really gives us hope that a more complicated model in more than 2 dimensions will really be able to separate these very well. And I ended up using XGB classifier for that. Now down here, I looked at mutual information regression to see if I wanted to keep them all or maybe just use a subset of features for regression. So the most important features were number 1, mileage, number 2, how long was the vehicle listed. And as you can see, the log, transform, and the regular one were the same amount of importance. It didn't matter. Then package. I don't know where that came from. It's probably got to be one of those TF-IDF features because I honestly don't know what was in there. I didn't explore them. Warranty is important. The word to, I guess. I don't know. All right, whether or not it was a luxury car. This is not the vehicle trim. This is from the TF-IDF vectorizer. But that ended up being important. The number of review counts, the seller review counts, that was important as well. Whether or not the car was clean, I guess. Maybe clean title, I don't know. 4-wheel drives were important, things like that. Now, for modeling trim, I needed a label encoder in order to model the trim because XGBoost does not automatically do well with categorical data. It just doesn't. You've got to one-hot encode things, and you need to encode the target labels as well. And so XGBoost classifier has a built-in use label encoder parameter, I guess, but it is about to be deprecated. So I decided not to use that. I just used the scikit-learn label encoder, and I think that was the right idea. So once I got the target one coded trims, then we're doing cross-validation. And going through here, we're just picking out the training data and the train data. Because these are randomly distributed, it's not like a time series or anything, we could just use train test split. Or CV fold, get everything there. And we're getting a train set and a test set for each one, fitting the XGB classifier, set this equal to false. Use label encoder equals false because if you don't set that to false, you get a warning that says, please don't use the label encoder. Just label encode yourself. And using M-error as the evaluation metric, running through that, bringing out the predictions, the predicted probabilities, and the ROC scores. And as you can see here, the AUC scores for each one, this is on the validation sets, were really high. It's fantastic. 0.988 is huge. And since this is multi-class, we're using one versus rest. So it's a form of average there. Going down a bit more, we've got ROC plots. I wrote the function that makes this plot underscore RO multi-class ROC. That function exists over here. And really all it does is cycle through the classes, get the true and false positive rates and the ROC curve there, and then just kind of plot it. It's not very complicated. If you want to pause, you can see exactly what it is and make it yourself. Now you go through and look here. They're looking great. They're looking great. They're looking great. Probably the lowest one out of all of them is this orange guy, which is the ROC curve of class 1, where the area under the curve is under only 0.93. But that's still fantastic. And I wanted to look at classification reports as well. It's always a good idea, even if you're not really interested in maximizing any of those metrics. But it can really tell you what's happening inside your model. As you can see, we're doing pretty well, but we got a really low number of class 4. So whatever label 4 is, there were only 4 instances of them in the validation set here, but it got all of those correct, so that's cool. Further down, this is why you really want to look at the classification reports. You can see label 1 had 9 observations and it guessed 0 of them. So it never guessed label 1 in this fold. It's always a good idea to look through there and see what's happening. Now, for hyperparameter tuning, I tried grid search CV because it's such an easy, just way to do things generally. But it was taking forever. I waited maybe 4 hours and said, I've had enough of this. I'm not doing this anymore. So I turned to Bayesian hyperparameter tuning using HyperOpt. It's very cool. It's a great way to tune hyperparameters for XGBoost models because it is quick. All right, it uses so you define a prior distribution for the different parameters, hyperparameters, and then it runs different models and everything and uses Bayesian statistics to update and get posterior distributions to try to kind of zero in on the expected value that is the best parameter. And we can kind of watch that down here. I needed a couple of other functions for this. I wrote this one. We'll go look at that in a second. As you can see, it ran about 100 times, I think. And I told it to print the accuracy and the AUC every single time. And as the loss function down here, the best loss, I told it use the negative of the area under the curve. So whatever you call loss, it's going to try to minimize. I needed the highest area under the curve, so I'm minimizing the negative of that. Let's go look at that function over here, hyperparameter tuning. So first, here we had optimize, okay? It takes in a hyperparameter space that is this here, all right? The prior distributions for each of the parameters. Then I said I want these to be global functions because I need to feed them into these other functions without calling them again, without feeding them into it. So I need them to be global. I'm getting a train test split on the features and the target. And if regression is true, then I want to run my regression tuning function from up above. And if it is false, then I want to run the classification tuning function up above. And then the function from HyperOpt that actually does the optimization is called fmin. All right, so it's going to call one of these two functions, and then it's using that hyperparameter space, and it's using this way to do it. It does 100 evaluations and saves these trials and returns the best hyperparameters as determined by the fmin function. Let's go up and look at classification tuning. So what it's doing here is it's starting an XGB classifier model using the hyperparameter space to set all of the hyperparameters in there. Now it knows it's got an X train, Y train, X test, and Y test, these different pairs to evaluate the performance of the model on, and we're fitting it on X train and Y train, and our evaluation metric is going to be the area under the curve. Early stopping rounds just to kind of speed things up a little bit. Then we're getting the predictions, the probability predictions. I want to see the accuracy and the AUC score for each one. And then down here, you need this very much with HyperOpt. You've got to return a loss function, okay, that goes into fmin. So the fmin function down here knows it is trying to minimize this loss that comes out of this function. And then status, I've just always seen hyperopt use status okay, so I left it in. This one is not actually required, but I wanted it to return the best model so I wouldn't have to retrain. That's fine. The regression tuning function is exactly the same, except it's a regressor instead of a classifier. And then I'm using the mean squared error or root mean squared error and R2 scores instead of accuracy and area under the curve. So we're not going to come back and talk about that one. It is the same. So after this ran, it said that the best loss was negative 0.95 or an area under the curve of about 0.95. And now I can fit a full XGB classifier model with the best hyperparameters. And I'll fit that, run it. This is how well it performed on the training data because I trained it on all the data. All right, it got a training AUC of 97.22% and training accuracy was about 77%, which is great for how many labels we have. But as you can see, it never guessed number one. Never. There were 54 cars that were label 1 and it never guessed it. There were 123 cars that were label 5 and it never guessed it. There were 23 cars that were label 4 and it never guessed it. So if we get any cars from those labels in the test set, we're just going to get them wrong. All right. Now I wanted to look at the feature importance because that's usually something that places will care about. Jeep versus Cadillac was very important. The condition of the car was important. FM radio, important. Audio equipment, important. All right. Used, important, apparently. So a lot of this was from that TF-IDF. Heated, all right. Heated seats, important. Front wheel drive, apparently I should have kept that because that was important. The year, maybe, things like that. So interesting that so many of these came from the just that bunch of words, that little text column. Audio and Bluetooth were from the vehicle features that we one hot encoded earlier. So I'm glad we ended up doing that. Now I'm going to predict the trim for the data set. It goes kind of the same, blah, blah, blah. So we get the test data. This is important. All right, we're just looking for it. It's got no missing values. And we use the process test features. All right, it's important that you do everything exactly the same on the test features. So that's why I wrote that separate function, because it just does everything the same. And then I could just fit a model to it. All right, and get the predicted trims and the predicted probabilities for the trims, which I needed later. And we'll talk about in a minute. Now, after you've made your prediction, you want to say, does this make any sense? So looking at the proportions of what was predicted in the training set and what we predicted in the test set, or the ones that we know versus the ones that we guessed, we want to see how different are they. And I think they're pretty close. We had about a third of them were limited in the training set, and we guessed, nearly half of them, but a little less than half of them in testing. We had, 7% overland, but we only guessed about 3% overland. But that's not too big a difference, and I think that these predicted distributions look close enough that I'm not too worried about it. If we were getting like 33% training and 70% in testing, then I'd say something's wrong with our model. We're not doing a good job here. But these look pretty sane. Now for dealer listing price, we didn't have to do too much. But what I figured was the trim is probably important. Okay, trim is probably important to the lister price because the highest, fanciest SRT Grand Cherokee is going to cost way more than the Limited or the Laredo. So I one hot encoded the trims and then concatenated that on to the features. So now I have 231 features because I've got one hot encoded trims on there. And then went straight into modeling pretty much because I've already pre-processed all of the features. Using the same cross-validation technique. Look at this here, our R2 scores were in the low 90s, which is great. Then down here, all I did was plot the performance on the validation data in each cross-validation fold. And here we're graphing predicted price on the y-axis and listing price. So we really want those to be, along this straight line, and they're pretty close. We want these to be centered around 0, and we'd like them to be small, but they kind of spread between negative and positive 5,000, kind of a lot. And then we've got the root mean squared error here is close to 2,000. The median absolute error is closer to like 1,300, and the median absolute error is a little under 1,000. So we've got a bit of a skew in our errors, which I think is interesting. And all of the folds performed very similarly. Again, we're using a hyperopt for that hyperparameter tuning. It was basically exactly the same except for the metrics being RMSE and R squared. So this ran and gave us a best R2 score of about 0.95, which is awesome. Going down, I'm just going to use the best hyperparameters to fit a model here. And fit it. Then I'm just kind of looking at how did it perform on the training data. So this is on the training data. We expect this to be kind of, overfit a little bit. Maybe not overfit, but really strongly fit. So everything's directly on the line. Awesome. The residuals are plus or minus 500. Awesome. The RMSE is like under 200. It's under 175 here. Great. But we expect this to be better performance than it's going to have on the test set. Now I got the feature performance on the price. And whether or not it's a Cadillac is very important. Track hawk, very important. All-wheel drive, important. 6.4, big engines, important. Is it a Laredo? Because those are lower priced. Is it a Limited? Because those are kind of lower priced. What year is it from? Things like that. If it was a fair price or not was pretty important. So I think it's interesting that for the trims, the text data was super important, but for the price, it was not. I think that's pretty interesting. So now we're going to predict the prices for the test set, but the issue here is we don't know the trims for the test set, and we used trim as a predictor, all right, as a feature for our price model. So what I decided to do here was I don't know the trims, but I can predict the probability of each trim. So I can find the expected price by getting the expected price given it's in a certain trim times the probability of being in that trim. And that's what we did. That's what I did down here. So I got the test features and appended columns, and each column has each column represents a trim. And then what I did was I set, say, the first trim column is all ones. So now every car is in trim 1, and I predicted the price. And then I set every car is in trim 2, and I predicted the price, and so on until I gone through all of the trims. And so what I then had was a data frame of prices down here. And now to get the series of prices, of predicted prices, I need to go through that data frame of prices column by column. All right, and I need to multiply that column by column with the probability of being in that trim. All right, so this line here, hopefully you can read it, that is what executes this function there. The expected value of the price is the sum of the expected price given you're in a trim times the probability of being in that trim. And now that we've got those predictions, we need to do a sanity check. So we're doing descriptive statistics, training versus testing. Means are very close, about 32,300. Standard deviations a little lower on the testing, which means we're just going to get a lot more centralized predictions. We're going to miss some of those outliers. We got a higher minimum. We got a lower maximum that goes with that standard deviation. Our medians were very close together, about 31,300. And even our 75 and 25th percentiles were pretty close. And then I'm just plotting those together. So you can see these blue ones, that's the that's the actual values, all right, or the training values, sorry. And this green one is the predicted prices. And you can see that they're close to being the same, but the predicted prices end down here, whereas the training prices go way up. So now, again, when I actually did this challenge, I didn't have access to test data answers, but I split it earlier specifically for this video so we could look at how it performed on completely unseen data. So down here, I just got the test ROC because I know the final answers in this case. And using one versus rest, I got an AUC score of 95%, which is fantastic. It's really awesome. And the accuracy is about 74, which is great. But down here in the classification report, like I said, we guessed 0 of the high altitudes. We guessed 0 of the track hawks or the trail hawks. If we look at this confusion matrix, we would like for all of the values on the diagonal to be in some kind of blue. We didn't get that. And part of that's because we had pretty unbalanced data. You can see we had about 320 correctly identified whatever number 8 is. And we kind of missed some of those too down here. 8s and 2s were maybe a little hard to tell apart. Then down here, we're getting the RMSE, the median absolute error, and the R2 score, all right, for the prices. And these were significantly lower than on the training data or from our cross validation. So, so it looks like we kind of overfit the model when it comes to predicting the price. But how could we possibly have known that if we didn't know the test set answers? All right, so our RMSE was almost $4,000. The median absolute error was about 2,600, and the R2 was only 70%, whereas when we were doing the cross validation, it was at like 95%. 70% is still pretty good. I mean, yeah, I think it's still pretty good. And then down here, look at how the model performed. Again, we've got a lot of values bundled around the line, which is great, but we've got these weirdos over here that had really high actual prices and fairly low predicted prices. And as you can see, our residuals are skewed, left skewed, and these are much higher. It's hard to tell maybe, but these are actually much higher than they were in the cross-validation. Now down here we can compare the distribution of predicted prices versus true prices in the test set, and they look pretty good actually. Look at this. It's got this little bump right there, and this has got a little bump too, maybe not as big a one. But I think that looks very nice. And it's another way to see them, just put them on top of each other, and you can see they look great. So really, I'm very proud of how this ended up, even though we maybe got a little bit of overfitting. I think it's an interesting approach to an interesting problem that I think went really well. Down here at the bottom, for the actual predictions, I had to put them all into a data frame that had the index number, then the predicted trim, then the predicted price, and offload that into a CSV file. But that's it. I think it was a very interesting problem, and I think I found a cool way to handle it that honestly didn't take that long. So let's go back to in person and we'll sign off.
So after seeing that, sitting through that whole thing, what do you guys think? What could I have done? We saw some overfitting in the end there when predicting prices. So what do you think we could have done to prevent that? Off the top of my head, I could think maybe if we hadn't used trim as a predictor, we wouldn't have had to deal with the uncertainty surrounding the trim, and that might have gotten us somewhere. Because we knew for certain the trims in the training set. Maybe what we could have done was use the predicted trims, use the predicted probabilities of each trim from the training set instead of one-hot encoding the trim. That might have helped quite a bit, actually, and then we could have just input the probabilities from before. I think it's a cool idea. I think I am going to try that, and maybe I'll do a follow-up video here in a few days and let you guys know how that came out. But if you think of anything else, I would absolutely love it if you left me a comment about it. What would you guys have done differently? What did you think was a good idea? What was a bad idea? Would you have handled that column of text data differently? I just did a TF-IDF encoder because it was fast and it was easy and it gave me something I could work with out of that column. But there are a lot of different ways you could have handled that. So let me know in the comments if you guys learned something. Go ahead and give me a thumbs up. And if you want to keep learning with me, subscribe to the channel. And like I said, that linear regression super fast course is going to come out real soon. I'll see you guys later.